please.
Okay, so thank you so much for inviting me, for having me here, for giving me the opportunity to really talk about this. So as Boris said, this talk will be about model theoretic classification and its application to algebra. My aim is to give a little taste on of model theory and to show some applications to classifying algebraic structures and classification and application in general. Okay, so as promised, I will assume nothing with respect to logic and model theory. So let's start with a few definitions. And please stop me in any time if you have any questions. I'll be more than happy to answer. First order language is a collection of symbols for relations and functions. So relations are any relations on the structure itself, on the set itself, and functions, okay, we know what functions are, together with the symbols of elementary logic. And what I mean by that is equality exists for all, conjunction, disjunction, and negation. Let's see some examples. Language of groups, we have one two-array function symbol, which is the multiplication, and one zero-array function symbol. A zero-array function symbol is just a constant. I'm not giving any interpretations right now for the symbols, just examples of languages and examples of symbols you can get. Language of rings, we have two array function symbols, addition and multiplication, and two constants, 1 and 0. Language of valid fields, it's the same as in rings, but we add another symbol, which we usually use to define the ring of integers. But the valuation ring, I'll talk more about it later when we talk a bit about valid fields. Language of orders, just one relations symbol should be the order. And you can combine it and say for ordered abelian groups and have the addition, the identity elements, and another relation. What can we do with those? A first order formula is anything meaningful. When I say meaningful, well, I believe you can understand what I mean by that. Write down with the symbol of the language. A sentence is a formula without any free variables. Let's see some examples. Say in the language of groups, we can write down for all x there exists a y such that xy equals e, the identity. Okay, what it means is every element, okay, when we interpret it afterwards in a meaningful structure, it would mean, of course, that every element has a right inverse. This has no free variables. All the variables are quantified over. Language of rings, we can say exist y such that xy equals 1. X now is a free variable, and now, so you can ask which element in our structure satisfy this formula. So all the elements that would satisfy this formula are elements that are invertible, right? You can say in language of orders, Z is less than X, less than Y. Now you have three variables. Oh, yeah, okay. These are the examples here. And the first order structure is in the language L is a set, and you give interpretation to all the symbols. So if you have an interpretation for addition, you can interpret it as addition. If, for example, you are in an abelian group, but of course you can interpret it any way you want. But mostly we do it in a meaningful way, so you'll know what I'm talking about. For example, the group S3 in the language of groups, when we interpret the identity element as the identity and multiplication is normal multiplication. Polynomials over X is a ring, interpret it as we would. And Q plus and less as an ordered abelian group. A consistent theory in a language is a collection of consistent sentences, which means that for me, right now, a collection of consistent sentences is just a collection of sentences that you can find a model, you can find a structure that satisfy all these sentences together. So for instance, if you take the axiom of groups, say normal, just groups, then it's consistent because you can find groups that satisfy all of them, say S3. They satisfy all the axioms. So all these axioms together, the theory is consistent. If we have a structure, we can look at the theory of M. That's the collection of all sentences satisfied in this structure. For example, since the integers are commutative, this sentence that says that it's commutative will be in the theory, but of course, it's not a sentence in the theory of say, the matrices, the real matrices, when you take n larger than 1. Okay, questions up until now? Okay, good. So let's delve into our main definitions.
I'm sorry, can you go to the previous slide?
Yeah, sorry?
I had a
yeah, of course.
Small question. So it's supposed to be
yes.
y equals yx. Is it a typo here?
Oh yes, of course, sorry. Okay. You go over and read something for 20 times, and then of course you miss something like this. Yes, xy equals y. Okay. So Sharon Shelah from the Hebrew University started already in his PhD thesis. Okay, his goal was something else, but while proving his PhD, he initiated a classification of first-order structures by means of combinatorial structures they exclude. So I'll give examples, but what do I mean by that? So say you have a formula, so phi, and you have 3 variables. Say you have 3 variables, it's a tuple of x, and then you separate them into 2 sets of sequences of 3 variables. One of them calls them the x, and the other one calls them the y. Now this gives you a relation, right? A relation on M, on the structure. Because now you can take a pair of tuples, say A and B, and ask if they are satisfied by this formula. This gives you a relation. Every time you have a relation, you can ask, okay, it's a relation. Can we embed some combinatorial structure into this relation? Can we embed a graph, a tree, a certain kind of graph, a random graph? Can we embed other kind of combinatorial structures? And usually, and that's the real insight here, there are some kind of meaningful classes of combinatorial structures that when we can't embed them into the relation, you can actually say something very meaningful about the structure, about the theory. So we'll give some examples. Okay, so let's see. First definition. Let's say we have a structure M. And now we have a formula. We partition the 3 variables, x and y. We say that it has the order property if for every n, we can find 2 sequences of tuples, a's and b's, such that ai and bj are satisfied in this formula. Phi ai bj satisfied, it holds in M, if and only if I is less than j. Okay, so this is a bit awkward when you see it at first time, because A, what does it mean? But B, we can give it some kind of interpretation using the relation we said before. In other words, there is no bound on the size of half graph we may embed into the relation. What do I mean by a half graph? A half graph is a graph of the sort of the following form. Okay, so we have A0, A1, A2, A3, A4, right? And we have B0, B1, B2, B3, B4. Now, half graph is something that okay, we will draw an edge every time that I is lesser or equal to j. Okay, so you have an edge here, an edge here, 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 and so forth. You have an edge here, 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 here. Okay, and I think you see what's going on. And so on. This is a half graph. Yeah, I have very good drawing capabilities. Now, every time you can, and we say that it has the order property if we can embed large as you want half graphs into the relation that phi defines on the structure. Okay, so you can say, so what, right? And it turns out that this is a very, very strong assumption that tells you a lot about the geometry and the algebraic properties that your structure has. And we'll see it in a minute. The definition is the structure is stable if no formula has the order property. If you can't find any formula such that the relation that it defines on the structure, you cannot embed, there is a bound on the size of half graphs you can embed into it. Okay, let's see some examples. Examples of usually the most well-behaved structures that we can find. Infinite sets, so it just means, what do I mean by infinite sets? The language is just equality, and the theory says, I'm infinite. I have more than one element, I have more than two elements, I have more than three elements, and so forth. Just sets, infinite sets. Abelian groups, free groups, which is a very, very deep theorem by Yatir, that they're stable, and separately closed fields, or if you want, algebraically closed fields. They're also stable. Now, to prove any one of these, of course, you need to know something about the formulas that are satisfied in the structure, and then see if you can embed large enough half graphs as you want. There are more equivalent definitions, there are other equivalent definitions to stability, and we can use that, but I won't introduce it here. And now let's see a nice application of this. I claim that if we have a stable integral domain, so it means that if you have an integral domain in the language of rings, and you know that the theory is stable, it must be a field. Every element must be invertible. But really, yeah, so let's give the proof. But really, you'll see that we need even much less instability to do that. Okay. So let's assume that you have a stable integral domain, and we'll now consider only one formula. We only actually need to use one formula, that only one formula doesn't have the order property. So let's take an element, A, which is non-zero, okay, and assume it's non-invertible, right? And now consider A squared, A cubed, and so forth. They're all different elements, right, because it's not invertible in your integral domain. I claim that phi ai aj if and only if I is less than j. Okay. So one direction, if we know that phi ai aj, then what do we know? We know that there's an element z, say c, right? That equals to aj. This is what it means. But we're an integral domain. Okay, so yeah, so I'm to assume that I is strictly larger than j. But we're an integral domain, right? So this means that ai minus aj c equals to 1. That's a contradiction, right? Because we assume that it's non-invertible. The other direction is straightforward, right? Because if I is less than to j, then of course if we take ai and multiply it by aj minus I, you get aj. So you see, the proof is very simple. We really didn't do a lot, but from the fact that we know that we can't embed a certain combinatorial relation into this formula, specific formula, we could already say a lot, that it must be a field. Okay. Note that even we used here something even less than stability. We only use the fact that if we look at these ideals, right? Okay, so this is here, right? If we look at these ideals, it must stabilize at a certain point. Okay, any questions? Okay, good. So stability is one very important domain in classification theory, and it got a lot of attention up until the 70s, 80s, and model theorists use this, the machinery developed there to do a lot of things, and we'll give a little bit of examples later. But another complementary domain in classification theory is that of dependence, which I'll introduce here. And this will be the only two real definitions that I'll give. So let's MB a structure. A partition formula like this, phi xy, is said to have the independence property if, again, for every n, we can find the elements a1 to an, such that if the and elements bi, which are indexed by subsets of 1 to n, such that phi ai b capital I holds in M if and only if I is an element of I. What does it mean? Okay, like most things in life, once you draw it, you know what it means. Okay, so we have a set, a finite set. This is our elements. Okay, and now you choose any subset of these elements. Say you choose A2 and A3. What it means that you can find some bi, so this will be B2, 3, right? Such that the only elements from our finite set that are satisfied by this formula is exactly 2 and 3. And you can, if you'll allow me to use this terminology, shadow any part of this finite set by this formula. Every time you choose a finite subset of our A1 to AN, you can pinpoint, you can choose only these elements to be instances of our formula. I use shadow because there's a connection to machine learning. This how do I, okay, maybe I'll have to clear it first. Okay, in machine learning there's a dimension called Vapnik-Chobonenko's dimension, VC dimension, and it exactly means that this family of sets that you can get, the VC dimension of it is infinite. It means that every time you choose a large, as you want, finite subset, our formula phi can always pinpoint any, can choose every finite subset of our set. So this notion of VC dimension was defined independently in model theory and in machine learning and in combinatorics around the same time. M is dependent if no formula has the independence property. So it means that every time you choose a formula, there's a bound on the finite set that it can shadow. You can't find large enough finite sets. So you see, as in here, as in before, in the definition of stability and dependence is a purely combinatorial definition about things that you can do in combinatorics. But it turns out that the implications, algebraic implications and combinatorial implications, or in any structure you choose, is sometimes vast. It tells a lot about the geometry of this algebraic structure. And we'll see some examples. Questions about this definition? Okay. First, let's give an example, some examples. So for first example is stable structures. Okay. So why is every stable structure also dependent? Okay, it basically boils down to the following fact, that I is less than j. Okay, if and only if I is in 1 to j. Right? So if we have our sets as before, then this holds if and only if I is less than j. So every time you have a configuration that gives you the independence property, you can also find a configuration that will give you the order property. So when you take the negation, right, every stable structure must be dependent. Other examples are the p-adic numbers. Okay, what do I mean by p-adic numbers? Okay, assuming probably most of you do know it, but it's a good opportunity to give a definition. So a valued field is a field together with a valuation. Evaluation, I mean a group homomorphism from the multiplicative group to some ordered abelian group that satisfies the non-Archimedean inequality. Okay, so the p-adic numbers are just a completion. There's like a completion you can do as in metric spaces of Q, also, together with the p-adic norm, p-adic valuation, which just tells you how much, what's the exponent of P that lives inside Q. Okay. Any linear order is also dependent, but also any algebraically closed field, and you choose any valuation ring on your algebraically closed field. This is also dependent. Now, as before, let's give a nice application of the definition to integral domains. Every dependent integral domain has finitely many maximal ideals. Let's see why this is true. Okay, assume there are infinitely many. Really, as a proof will show that all we will actually show that there's a bound on the number of maximal ideals, and this bound will be the VC dimension of the formula. But we didn't talk about what is VC dimension, so let's just assume there are infinitely many, and we'll get a contradiction. Okay, so let's look at the same formula as before, which means that x divides y. Now, if we assume that it doesn't have the independence property, it means that there's some n, right? By something doesn't have the independence property, sorry. So this means that there's some kind of bound on the finite set that you can shadow. Okay? And let's see that exactly that will get a contradiction. Okay? Because let's choose elements AI that lives in the maximal ideal MI, but not in the finite union MJ, not in I. Okay, so this has to be J from 1 to N, but not equal to Y, to I. We know that there are such elements by the prime avoidance lemma, right? Every time that an ideal is covered by a finite union of our prime ideals, it must be contained in one of them, right? But maximal ideals are not contained in each other by definition, right? So you can always find an element that is in the maximal ideals, one in the certain maximal ideal, but not in the other. They form an anti-chain. But now, if you choose any subset of 1 to n, let's consider the multiplication of those AIs. Let's see that this exactly gives us what we want. Okay, so we want, right? Phi AI BI if and only if A is in I, right? This is what we want to show in order to get a contradiction to dependence. Okay, so let's see, one direction. If this holds, it means that we can find some kind of C. This is equal to B large I. But this means that B capital I is in the ideal generated by AI. So it means it's in the maximal ideal I, because AI is in MI. But it's a prime ideal, right? So exists a J in the I such that AJ is in MI. Okay, so this is a contradiction. Contradiction, okay, yeah. Sorry, not a contradiction. I didn't want to say contradiction. Yeah, so BI is in here and here, yeah. So it means, well, let's draw here. Yeah, it means here. It means, right, that I was in I, right? Because the only element here that's in your prime ideal is AI. Now the other direction is straightforward, right? Because for the other direction, if we know that I is in I, then of course BI is in the ideal generated by AI, but just by definition. Okay, so just by assuming that the theory or even that the formula here is dependent, we can already say something meaningful about the algebraic properties of our structure. Any questions? Okay, good. Let's continue. Okay, so this is the universe as proposed by model theorists. Red dots are just examples that we have. Maybe I can, did I open it? Yeah, okay. So this is taken from this webpage, and Gabe Conant was kind enough to allow me to edit. So you see, all these red dots, oh, I'm still in the annotate. All these red dots are just examples. So say this is the real closed fields. This is free group on at least two generators. This is set theory. This is just normal integers. And we work very hard on classifying all these structures based on what we know. Okay. And so let's put it into context. Okay, here. Okay. So right here, these are all the stable theories. So you see stable. All of this large rectangle, this is dependent. Okay, it's called NIP here, but this is all the dependent theories. Over here, this is something called NSOP1, no strict order property, here. And now each one of these, let's say, quadrants, or at least domains, are even more classified, finely classified. So in stability, we have, say, super stable structures, which means that you have some kind of rank or dimension around that is bounded. Omega stable is that you have even more meaningful dimension, something that behaves like the risky dimension around. We have here the dependent structure that we talked about before. Here you have something called DP minimal, that you have a rank on the dependent structure, which is rank 1. This is what's meant by minimality. But you can also have finite DP rank, that it has a finite rank, and so forth. So model theory today, as a whole, is about classifying structures and finding where they are, where they fit in this classifying, in this universe, and classifying them into tame versus wild structures, but also studying each one of these areas by itself and trying to understand what unifies them and what kind of geometry and independence relation really pop up in these structures. So I want to give some examples of applications and then really delve into a certain kind of applications that are present shortly. Okay. But if anybody wants to go to this webpage later and check it out, it's pretty nice, and it might give you a feel a little bit of what this means. You can choose any one of these areas, and it will give you a list of known examples that we have and some kind of properties that we know, and so forth. Okay. So nowadays there are two main directions for applications of model theory. The first is realizing that some known structures are tame. It means are dependent, stables, omega stable, super stable, finite DP rank, NSOP, all these fancy names that we saw before. And then once you realize that they are tame, to use the tools that we have for model theory. One very famous example is Udi's proof, Olszewski's proof of Bar-Ilan, which is a conjecture from algebraic geometry. I won't give any, I won't even say what it means, but for those of you that don't know what it means, it might say something. And a critical point of the proof really was that he got some kind of structure, and then he said, okay, I know that it might be a complicated structure, but I know that it has very nice model theoretic properties. Say it's one-based, locally modular, other fancy names, and now I know a lot about it. I know about the geometry inside, and uses some tricks really for model theory in order to continue. The proof is much more complicated than that, of course. Another recent example is a generalization of Elekes-Szabo to arbitrary reality and dimension by Martin Weiss and Bulliard. And again, this is a theorem in combinatorics. So again, usually people from combinatorics say, okay, I have a graph relation or a relation of incidences of lines and points in the plane, and I want to bound the intersection number. Model theorists will look at it a little bit differently. I don't really care about only the relation, the graph relation or the incidence relation. I care about formulas. And now that I only care about formulas, I relax a little bit my assumptions and I can say much more. And another recent example, which I am giving here, but it's nowhere near the caliber of these two first examples, just to say that it's connected to something we already saw. A recent example is by Philip Dittman and RFM, is the set of algebraic extensions of Q in which you cannot define either the integers or the set of algebraic integers, which means, what do you mean by define? You cannot find a formula that gives you exactly this set, is meager in 2 to the algebraic closure of Q, taken, say, with the pointwise convergence topology. A critical part of the proof was that in a certain class of fields, every definable ring is a field. So what is a PHC field? A PHC field is a field in which every absolutely irreducible variety has a rational point. So it's something a little bit weaker than algebraically closed, but it's still, how would I say it? It still has enough structure inside it. Omega 3, you can forget it. It just says something about the Galois group. But they use the fact that you can't define that every definable ring there is a field. Now, basically, we saw the proof, because it's the same proof that we showed that every stable integral domain is a field. But once you know that these kind of fields are tame model theoretically, you can automatically just use what we know. Another direction of application is now taking an abstract algebraic structure, say group, ring, field, valued field, whatever, and assume that it's tame. Say, assume that it's stable, assume that it's dependent, assume that it's strongly stable, super stable, or whatever. What can be said about its algebraic properties? And we saw two examples like this, when we saw that every integral domain, stable integral domain must be a field, and every dependent integral domain must have finitely many maximal ideals. Now there's a whole host of these kind of properties. Now how do we use it is that later when these algebraic structures pop in some kind of tame structure, we can use its result. What do I mean by this? Say you have a very large structure. It could be a field, it could be a graph, it could be some kind of metric structure if you use the correct language. And now you find a very small structure inside, a very small definable set. And we see that it's a field. See that it's the integral domain. From the fact that we know that the large structure is stable, say, it automatically means that the small structure that we found inside is also stable. So it must be a field, because we know that every integral domain which is stable must be a field. So every time that you find this small structure in a very large tame structure, you can automatically say something about its algebraic properties. Because tameness is something that is usually inherited by moving to definable things or interpretations. And what I mean by interpretation is even looking at quotients by some kind of equivalence relation. Now, it might not surprise you that I'll focus on the second application, right? Because I only have an hour to talk and not 2 or a seminar. And so I can't really give proofs of more complicated stuff, but it would be a nice way to actually see what kind of properties we can just deduce by assuming some kind of tameness conditions. Any questions? Okay, good. Okay, let's start off on stable fields. What do we know about fields? That the only assumption that we have on them is that their theory is stable. Okay, not much, right? I'll start. But let's assume that we are an omega stable infinite field. So recall I said it in passing that omega stable means that we have a dimension which behaves something like the Zariski dimension. What I mean is that if we have something of dimension 3, we can't cover it by infinitely many disjoint sets, which all of them have dimension 2. That the only way that you can cover it by infinitely many parts of less dimension is that if it's infinite many. So the only way that you can cover a plane by lines is that if you take infinitely many lines. You can't cover it by finitely many lines. This is what I meant. McIntyre in the 70s showed that if you have this kind of dimension around, the field must be algebraically closed. Now, how did he show it? He showed it that as a consequence of this assumption is that the map sending x to the n, the exponentation map, power map, sorry, and the Artin-Schreier map must be onto for any such field. But now we can also look at finite extensions of the field, right? Because every time that you have a field, what is a finite extension of the field? You choose a basis, and then you say, how do these basis elements, how do you multiply each other? But this is something that you can say in a sentence, in a first order sentence. So you know that finite extension of the field is also omega stable. And then you know that this assumption of them is the same. I mean, that also the power map is onto and the Alten-Schreier map is onto. And now you use Kummer theory and Alten-Schreier theory to show that it must be algebraically closed. So the proof is again a little bit more convoluted than that, but this is the gist of it. Not long afterwards, Sherlin and Shelach generalized this to superstable division rings. What I mean by superstable is that you're stable, but you have another rank around that is bounded. Around the same time, Carl Woods showed that every separately closed field is stable. So this begs a conjecture, right? Because we don't have any other examples, it turns out. Is it true that every infinite stable field is separately closed? We don't know. And it seems very much, it doesn't seem that we still have the tools to tackle this conjecture as a whole. But we do know it for omega stable and superstable. And myself and Daniel Palasin have shown that every infinite stable field, actually, division ring, of finite DP rank is algebraically closed. So if you have an infinite stable field, and there's another rank that comes from dependent structures, it's called the DP rank, and you assume that this rank is finite, then it must be algebraically closed. So that's another step in the direction. And recently, Johnson gave another proof of this result as a part of a much larger theorem. And much more recently, Johnson, Tran, Wolfsburg, and Yeh have shown that every large stable field is separately closed. What do I mean by large? So large is an assumption of fields from field arithmetic. It was defined by Florian Popp. It means that every time that you have a curve and it has a smooth point on the curve over the field, it must have infinitely many points as well. Okay, so maybe for the analysis in you, it seems weird. What do you mean by a curve that has only a few points, many points? I mean, it must be continuum, right? But if you look at it from an algebraic geometry way, you can have a curve, which is an object of dimension 1, but then you can ask how many points there is in the specific field, and of course, it could be finite. It could be 1. It could be none. So every large stable field is separately closed. Example of a large field is maybe not a trivial example, is an infinite algebraic extension of a finite field. This is a non-trivial example of a large field. Okay. What about dependent fields? What do we know about them? Okay. We know that the real numbers are DP minimal. So it means that they are dependent, and the rank that come with dependence is rank 1. I want to find the rank, right? At least I don't think so. This uses already quantified elimination results that go back to Tarski. Much more recently, the periodic numbers were also shown to be DP minimal by Dolic, Goodrich, and Lippel. We know that every time you have an Enzelian valued field, what is an Enzelian valued field? So we call this a valuation. And this valuation is called Enzelian if there's only one way to extend it to every algebraic extension. Equivalently, there's a way to lift simple roots from the residue field of polynomials to the field itself. They've shown that every time you have an Enzelian valued field, and you know that the theory of the residue field, only the residue field, without any more information, is dependent, it must give you that the whole Enzelian valued field is dependent. So it's a field with a predicate for the valuation ring. And recently, I mean, not very recently, I think 50, 60, 80, 18 years ago, Shelach gave the following conjecture. At least nowadays, it's interpreted the following way: that every infinite dependent field must be either separately closed, real closed, I mean, it has the same first order theory as the real numbers, or it admits some kind of Enzelian valuation. So it must be because it's something that we know very well, cell properly closed or real closed, or there must be Enzelian valuation around. This conjecture is very deep. It implies the conjecture about stable fields that, as I said before, we are nowhere close to solving it as a whole. But there was some kind of progress. So Johnson recently have shown that if we assume that the dependent field has finite DP rank, that the rank is finite, it must be algebraically closed, real closed, or admits the Enzelian valuation. So we've shown it for dependent fields of finite DP rank. Okay, so this is a huge step, and he uses very ingenious arguments to show it, but still to show it for dependent fields as a whole, still, it's a much larger step than that. There's another conjecture in this field that leads the way. It's called the Enzelianity conjecture. Say you have a field and you have a valuation on it, so a predicate for the valuation ring, and you assume that this theory is dependent. The conjecture is that it must be automatically Enzelian. So for those of you who know a bit about valued fields and Enzelian valued fields, it says a lot about the topology that this valuation gives. So recall that every time that you have a valuation, V, then of course you have the valuation ring, just the elements of positive valuation, but you can also talk about balls, right? Balls of radius R. So it gives you a topology. The conjecture is that if the theory is dependent, it must be Enzelian. Why do I mean that it's something really topological in nature? Is because an Enzelian valuation, if the valuation is Enzelian, it means that we have some kind of an inverse function theorem around, similar to Eddy analysis. This conjecture is true in positive characteristic by Johnson, using the fact that you have the Fubini's around. The Scheller conjecture from before implies this conjecture. This is a result by myself, Asaf Hasson, and Franziska Janke. It's actually equivalent to a topological statement, which means that every time that you have a field with two valuations on it, and assume that if you had the predicate for both these valuations, then it's dependent, then they must induce the same topology. The topology is the same. That's a result, again, myself, Asaf Hasson, and Janke. And we proved that if we assume that one of the valuation is Enzelian, it has an inverse function theorem, if you wish, an implicit function theorem, same. And then they induce the same topology. So we almost showed this conjecture as a whole, but we assume that one of them is Enzelian, which is a very strong assumption, but it's still a step in the direction. And it's a connected result, but not really under it. It's a connected result that if the field is dependent, respectively strongly dependent, which again means that some kind of rank is bounded, and you have an Enzelian valuation of the field, then adding the valuation to the structure, I mean adding the predicate, doesn't ruin its tameness. Because imagine, say you have a field, so you can say a certain kind of sentences and formulas. If you add a predicate for the valuation, the complexity of what you can say increases, right? Because you can now talk about the valuation, which you couldn't before. The theorem is that adding an Enzelian valuation doesn't ruin your tameness. If you were dependent before, you're still dependent. If you're strongly dependent before, you're still strongly dependent. So these are the two results, one by Sylvie Anscombe and Franziska Janke, and one by myself and Asaf Hasson. And they're connected, but somehow none of these results imply the other. Okay? What can we say about rings? We don't even know if every stable division ring is a field. in general. We do know if it's an integral domain, but if it's a division ring, we don't know that. On the other hand, we do have an example independent division rings which are not filled, say the quaternions. They are a dependent division ring which is not filled. What else do we know? Every stable commutative ring, not an integral domain, is a finite product of local rings. That's a very old result by Chernin and Heinken. Every dependent division ring of positive characteristic has finite dimension over its center. Its center is a field, so you can look at it as a vector space over its center. It must have finite dimension. That's a result by Milia. Actually, when you know that it's a finite DP rank, the proof is much easier, and it was given in a short note by Christian Delby. And for those of you that know a bit about division ring, you can also even show that it must be a cross product. It has a Galois maximal field. If you took some kind of course in non-commutative algebra, you might recall that there's a netter construction, right? That if you have a Galois extension of a field, you can produce from it a non-commutative division ring. And this means exactly that your division ring must be of this kind of form. And you can also show that every DP minimal division ring is a field. Recently, a result by myself and Christian Delby is that if you have a DP minimal domain, integral domain, so it means that the DP rank is 1, then it's very close to being a valuation ring. What do I mean by that? It's a local ring with a maximal ideal, so maximal ideal M. If you localize by any non-maximal ideal, it's a valuation ring, okay? But maximal ideal itself something more, you can't really say that. It is divided in the sense of Anderson and Dobbs. It means that if you look at it inside the fraction field, then the maximum ideal of the localization as a set is exactly equal to the prime ideal. And we give a complete characterization of when it is exactly a valuation ring. So it's a valuation ring if and only if the residue field, we call this in the local ring, the residue field is infinite, or it's finite, and this is a principal ideal. Or taking terms from valuation theory, it means that either the residue field is infinite, or you have some kind of finite ramification. Still okay with time? Okay. So in the few minutes I do have left, let's maybe say a few things about groups in general, and I think we'll conclude with that. So as for groups, we know that stable groups have Tame structures, that they have generic points very similarly to algebraic groups. There's not much known about dependent groups in general, but we do know that there are some kind of connected components that arise like there's a topology around. We do know, as I said before, that every abelian group is stable. We know that every ordered abelian group is dependent. And a result of myself and Daniel Palasin is that we give a characterization of when an abelian group is strongly dependent. We have it when this rank is bounded, the dependent rank is bounded. So if and only if there are finitely many primes P for which A mod PA is infinite, and for every P, there's finitely many N such as this quotient is infinite. And what do I mean by square brackets P? I mean the P torsion points. I mean all the points of this group that if you multiply it by P, you get 0. You need that this quotient is infinite. There's only finitely many N, but this is infinite. And we do it by really analyzing the definable set, the formulas that you can say within an abelian group. Together with Asaf Hasson, we gave a similar, not similar, but parallel characterization for ordered abelian groups. So we show that every strongly independent ordered abelian group, so some rank is bounded. We show that actually the rank has to be finite, not only bounded. And that it has finite spines. I don't really know if I have time to say what its spine of ordered abelian group is. But it says something about the chains of convex subgroups that you can have inside the ordered abelian group. That's how you can't have infinite chains of a certain kind. And as before, that for the only finitely many p's, such as G mod PG is infinite. Okay, so I know that I gave here a very long list of results, or at least model theoretic results, that, or at least model examples of model theoretic assumptions that give on algebraic structures, but at least I hope that what you got out of it really is that just assuming something about the combinatorial relations that the formulas give you can say a lot about the algebraic properties that these structures may give. And this is only about algebra. You can talk about combinatorics, you can talk about analysis, as in metric spaces, Poisson spheres, and so forth. And every time that we have this appropriate obstruction, but appropriate constraints on the relations, you can actually say a lot about these structures. And one of the real advantages of doing it this way is, let's see, some kind of example. Say in algebraic geometry, usually you use polynomials, right? And look about, and on zero, you consider zero sets of polynomials, and this is the varieties, and you can talk about dimension of varieties. But what model theory really allows you is not only to talk about dimension of varieties, but the dimensions of any definable thing that you can think of. Use any first order thing first order formula, it defines a set, it might not be a variety. You can still talk about dimensions, talk about independent relations, and it gives you much more structure into the structure that we started. So thank you. This is basically what I wanted to say. But if there are any questions, of course.
Okay, thanks very much. Any questions, comments?
I do have a question.
Yes.
In the definition of the order type, can you go to that definition when you define the stable and unstable?
Yeah, here. Yes, here.
Yeah, it's this one, yes.
Yeah.
So my question is very simple, because you have here a sequence of omega, of length omega. So if you want a sequence of length omega plus omega, does it make sense, or is that some kind of small subtheories or something?
Okay, so first note that I don't have here a sequence of omega. I only said that there is no bound. It could be that for n equals 10, you must find some kind of AI and BI that will satisfy it. For n equals 1 million, you'll have to find some other AI and BI that will satisfy it. I didn't say that you can find something of length omega. But this is where model theory shines, really, is that we have the compactness theorem. So everything that you can satisfy locally, finitely, you can find some kind of very large model that in it, you can find large enough as you want. So I'll answer your question, but just to give an example, say you have algebraic closure of the rationals, you can find a very large algebraically closed field that contains a C that has much more information, and you can satisfy much more things in it, right? You can answer much more questions in C. You have much more numbers. And similarly, if you want not only length omega, you want length omega plus omega, you can do it surely, but you might need to pass to some very larger model of your theory. But we don't really care about passing to something much larger, because all we care about is things that you can talk about in first order. And we will know that if something is true in first order language in the very large model, it must be also true in your very small model. So the answer is yes, but you might need to pass to something larger in order to really find it.
Okay, thank you.
Okay. Any other questions? Okay, if not, thanks very much again.